Okay, good morning or good afternoon, everyone. Today we have the pleasure of having Dr. Bei Jiang from University of Alberta to give us a talk on differential privacy. Professor Jiang is an associate professor in the Department of Mathematical and Statistical Sciences. She is a fellow and a Canadian Institute for Advanced Research AI chair affiliated with the Alberta Machine Intelligence Institute. She got her PhD in biostat from University of Michigan, and her research interests focus on Bayesian hierarchical modeling, joint modeling for multimodal health data, privacy preserving and fair synthetic data, statistical inference under formal privacy guarantee and fairness constraint, and federated statistical inference. She has also worked closely with collaborators in women's health, mental health, neurology, and industry partners to apply cutting-edge statistical learning methods to real-world applications. Without further ado, let's welcome Dr. Jiang.
Okay, thank you, Zhihua, for organizing the webinar and then for the invitation. So today, actually, I want to share with you one of my recent work. So the title says it's online local differential private quantile inference where self-normalization. So first of all, I want to actually introduce or talk a little bit about what's data privacy. So at least this is something I was wondering when I was like working in this direction. So for a long time, I think researchers believe that as long as we remove the directly identifying information like name and then maybe the address, then it is safe. But it is not the case. So there are many legendary disclosure incidents due to failed de-identifications. The most famous one will be this identification of the at that time Massachusetts governor's medical information. So this is at that time a former PhD student, Winnie, who is now a professor at MIT, but she did an experiment to show how actually she was able to use the public accessible data and released insurance data to actually identify Massachusetts governor's information, in the sense she can tell exactly which particular role in the data sets belongs to Massachusetts governor's record. So from there, she was able to, even though there was no name, but she was able to tell this is his data record, and then she was able to actually identify confidential information like health information and then also the income. But people may not always want to other people to have access to such confidential information. So this is a breach of the privacy. And it turns out that Sweeney further did additional study and then showed that 87% of the U.S. citizens are able to be uniquely identified if we release their zip code, gender, and birth date. Only these three pieces of information allows people actually uniquely identify 87% of the U.S. citizens. So this is actually something people learned. And then there was another very famous example, which is 2006 Netflix prize competition. So they invited researchers to improve the baseline recommendation algorithm. So the winner needs to be able to improve their algorithm by 10%. And then actually they will award the winner $1 million US. So this is very, this actually received a lot of attention. So their training data consists of 100 million user data and then the ratings on the movies. So each user, so basically in this data set, there are different rows, so corresponding to different users, and then different columns corresponding to the ratings to different movies. So a typical data set. And then they want to people to show on the testing data set whether they can predict this rating accurately on some like reserved testing data set. So because of this Radio Privacy Protection Act, then there was no information about the users in terms of their zip code, birth date, or even name. So people believe this is a safe data set or a private data set that they can publicly release, but it turns out there was a privacy risk as well. So this is a PhD student and his advisor at the time was able to actually identify individuals to real people, in the sense that they actually found that there was a IMDA website that also contains users rating on the on different movies, and then some users even posted their true name. So they published out that this is something this is not confidential. This is not as confidential as health data. So they actually post their name and then their ratings on different movies, and then from there they are able to link. So they, like I said, each row of this data set corresponds to different users, and then different columns correspond to their ratings of the movies, and then they are able to match the based on the ratings of the movie. So then they are able to identify which particular row belongs to which individual users, and then this actually end up with like a privacy breaches, and then there was a lawsuit, and of course there was no more Netflix challenge anymore. So so then the question comes to how we can protect privacy. So in this talk, so today I'm going to focus on differential privacy. So we add some kind of random noise to the released results to protect the privacy. I will talk about the details later, but there are other frameworks that actually we won't talk about, but also used in the literature to protect the privacy. For example, there are synthetic data generation methods where we don't release the original data, but the sampled value based on the confidential data. And then there are distributed learning or federated learning approach, which is to only communicate to the raw. Instead of releasing the raw data, they release the summary statistics, which in some sense is a protection of the individual data. And there's a earlier work like k-anonymity, which is to make sure that there are several users that share the same information. So based on that, then the attacker couldn't tell exactly which record belongs to that user, just since there are so many users share similar information. And then there are classical statistical disclosure control methods like data swapping, top or bottom coding. For example, instead of releasing your true income, maybe we can release a top coded value, things like that. So, so today I'm going to talk about differential privacy. But I also want to emphasize that so privacy, even though we have the need actually to protect the privacy, but privacy is never free. So there's always a trade-off, even no matter what framework that we focus on. So this is a trade-off between utility and the privacy. So what's utility? Utility refers to the accuracy of the released data in comparison to the confidential data. So we want the released information to be the released data to have similar information as in the original confidential data after some kind of privacy guarantee. So then in terms of like measures, then there are global measures and specific measures. So for example, if we are to release the data, then we want the distribution of the released data to be similar to the distribution of the confidential data. So that's global, some like global measure of the utility. And there are also specific measure. For example, if you do a regression analysis using the released data, maybe you want the coefficient to be similar to the coefficients obtained using the confidential data, because this is looking at a very specific analysis. So measures like that is called the specific measures. And then risk. So risk in this case is actually the likelihood of learning confidential information. And then there are identity disclosure and attribute disclosure. So identity disclosure means that whether the attacker can learn which particular record belongs to you. And then attribute disclosure is independent of the identity disclosure. This is just the likelihood of learning your information about the attributes. So it's always the case that if you want high privacy protection, then the utility is low, and then low privacy protection, then high utility. So in the literature, whenever people propose new methods, they always want to focus on like maintaining the same level of privacy while maximizing the data utility. Then, like I mentioned, there are traditional statistical disclosure control framework. So in that framework, we assume that we have all the directly identifying information like name, your true names and address. Those are information that can directly identify who you are, actually being removed from the confidential data set. But like I said, it actually took researchers some time to eventually figure out that this is not good enough. This is not safe enough to protect the privacy. So then in the data set, there are two types of, we say there are two types of variables, X and Z. So X variable will be some quasi-identifying information. They cannot directly identify who you are, but they can indirectly identify who you are. So those variables include demographic variables such as age, gender, those type of demographic or background information that a attacker can indirectly use to identify who you are. Or when I say who you are, basically which particular record belongs to you. And then there are non-identifying information. So the traditional statistical framework usually assumes that based on the X information, they can learn which record belongs to you. So then from there, they can learn your confidential information or simply identify which record belongs to you. So the focus has always been to perturb, or we call synthesize, the values of X variable to prevent identity disclosure. And then usually we don't change the value of other variable just because those variables are not used to directly to indirectly identify your information. So we keep those variables unchanged to maximize the privacy, to maximize the utility. So then when we say identity disclosure or re-identification, it means that when the attacker can actually tell which record belongs to a particular individual or learn information from that particular individual. Then you can tell there's some drawbacks of that because we have to make an assumption on attackers' prior information on the individual. So we always assume that the ill intention intruder already have access to some of the information about the individuals in the data set. So this is the biggest assumption that we have to make. So they know the values of the values of those quasi-identifying information, also called quasi-identifiers, for certain individuals in the data set. And then the goal is to actually identify which record belongs to those individuals in the released synthetic data set. And then we have also to make assumptions on which variables that the intruder already have access to. So in other words, you have to actually decide or make the assumption which variables are quasi-identifiers, which are not. And then for those who are not considered as the quasi-identifiers are not going to be used in the calculation of the disclosure risk. And of course, there are different risk definitions, and it seems that there's no consensus on which one is the best. So this is actually the big motivation for better privacy frameworks. So differential privacy is the one that's being recognized as probably the best available framework for privacy protection. So I'm going to show you the mathematical definition, but first, this is just some intuition what differential privacy is trying to protect. So first of all, differential privacy is a criteria of privacy. It's the definition or standard. So we always say we release something under differential privacy guarantee. So it's not the algorithm or it's not the technique, but it's a standard of privacy protection. So it has a mathematically guarantee that says the information leakage risk. So the risk of an individual have information leakage doesn't change whether or not this individual's information is used in the analysis. So this is probably a little bit too abstract at the moment, but again, so it's not protecting the absolute protection of individuals' information, but it's protecting the additional information that attacker can learn based on whether or not this individual's data point is used in the analysis. So basically it says that you cannot learn additional information about this individual, whether or not this individual record is being used in the analysis or not. So in other words, it means that anyone seeing the result of a summary statistics and the differential guarantee will not be being able to make the same inference about this individual's private information, whether or not the individual's private information is included in the input to the analysis or not. So this differential, this also explains, this also explains the differential aspect in this differential privacy. So this is whether or not your data record is used in the analysis or not will now increase attackers' private information about your private information. So next, I want to show you, this is actually the case. So remember, we want to emphasize that this intruder cannot learn additional information about you, whether or not your information is included in the analysis or not. So for that reason, we actually have to define two data sets, X and Y. So we have data set X and data set Y, and the differences is that so we have delta X and Y equal to 1. So this refers to the fact that the Hamming distance between the data set X and Y is 1. So it's always referred to as the two neighboring data set that differ by one record. So there are variations. So there are two different definitions of two neighboring data set. It can refer to the case where the two data set has the same sample size, but one value, one record value differ. Or it refers to the case that this two neighboring data set has, so for example, the Y data set Y has one less record than the data set X. So that means the difference is that one data record, otherwise they're identical. So this guarantee says that either you apply your algorithm fancy M on X or fancy M on Y, the probability that you get the same result is about the same. So imagine that if we let the epsilon value to be a very, very small value, and then based on the Taylor expansion, that just means e to the power of epsilon is approximately equal to 1. So then that just means the probability that we have the same results, either working with X or either working with Y, is about the same. So that means the attacker cannot learn additional information about you just because your record is used or not used in the data set. So, so then this parameter epsilon is known as the privacy budget. So, which means the information leakage or the harm to your private information. So the smaller the value of epsilon is, the stronger the privacy guarantee. And then how do we achieve differential privacy? So in order to, there are many existing mechanisms that allows people to achieve differential privacy guarantee. But in order to do that, we actually have to introduce this concept of global sensitivity. So global sensitivity, so this is a definition for an algorithm. So this F can be like sample mean, sample median, or if we run a linear regression, it could be the coefficient of a linear regression analysis. So instead of releasing the original value of those quantities F, we actually add some kind of random noise to this F so that it can satisfy differential privacy. But how much noise that we need to add depends on this released quantity itself. So for that reason, we have to define this sensitivity of this private quantity f. So it's the maximum of the L1 norm between this two quantity under two neighboring data set, X and X prime. So again, there are different definitions. Either it refers to the case that the two neighboring data set have the same sample size, but one value differ, or it refers to the case that one data set has one less data record, but for the rest of them, they are identical. So it quantifies this concept of L1 sensitivity of this F is the maximum potential change in the norm of this F caused by one data record. So you can imagine in the worst case scenario that under this differential privacy guarantee, you can imagine in the worst case scenario where all the attacker already have access to the rest of the data record, then by doing the differential privacy, they can still guarantee that your record is being protected. So then once we define the sensitivity, then we can accordingly add the random noise such that the variance, so the scale parameter is just equal to this delta F, which is the sensitivity divided by epsilon. So epsilon is the privacy budget in the differential privacy definition. So say we want to release F, but for the reason that attacker can actually learn something based on this this released F. For example, this is something I have talked about earlier, that in the worst case scenario, that if the attacker already know the data records for n-1 records already, but not your record, then by releasing F and the values of n-1 records, they can actually do some very simple calculation to figure out your record. But differential privacy actually want to prevent from that to be happening. So they add this Laplace noise. So the variance is proportional to the sensitivity divided by the epsilon budget. And then next slides, I will show you that if this is how we actually want to release the information, then it is indeed satisfying the differential privacy guarantee. So this slide is simply to show you that for the Laplace distribution, so this is the form of the probability density function, and then in the case that we have the center of this Laplace being equal to 0, and then b equal to 1. Sorry, I think this is s equal to 1. Then the Laplace distribution looks just like it's just a positive half line. And then that's corresponding to an exponential distribution scaled by 1/2. So this is just to tell you how the Laplace distribution look like. And then now I want to show you that after we add random noise from the Laplace distribution, and then the output is indeed satisfying differential privacy. So again, we have this XY two neighboring data sets. So we use delta XY equal to 1 to denote this is the two neighboring data set. And then the F will be some function. So that's, you can consider this F as a summary statistics based on the original data set. So then this Px, Py denote the probability density function of this two random mechanism. Remember, the differential privacy is a guarantee. And then we say algorithm M satisfy differential privacy. That means we add some kind of random noise. So for that reason, this algorithm is random. So then we have the probability density function for M working with X, and then the random algorithm working with Y, that the PDF will be denoted by PY. So in here, even though we didn't say clearly, But this is actually so this is the so when we say the PDF, this is the density function that corresponds to the randomness due to the noise, not due to the X and the Y. So this is everything that we talk about here is a conditional distribution given the data set X and Y. So then we want to compare the probability that we actually have the same result, either with X or either with Y. So that's the ratio of this PXZ and PYZ, meaning that either you use dataset X or use dataset Y, the probability that you have the same result, right? So remember the result is just original value plus some Laplace noise. So then this PDF is just based on the Laplace, the density function of the Laplace distribution. And then here, this is a general case where the released summary statistics F could be k-dimensional vector. So this is, and then we actually independently add noise to each dimension. So this is why we have the product I goes from 1 to k, and then and then here this exponential term is just due to the fact that we add Laplace noise to the output. So we didn't really consider the randomness of f of x, but just the run. So because this is a conditional specification, so then this two exponential term can be simplified into this this form. So then you can tell that this is the differences between this the differences between these two absolute value will be bounded by the sum by this form. This is just triangular inequality. And then next we do some kind of simplification by moving this product inside the exponential. Then we have the this form just equal to the L1 norm between fx and fy. So remember, that's exactly how we define the sensitivity delta F. So delta F is the maximum change of fx and fy for any x and y. So naturally, this numerator will be bounded by, so that this L1 norm will be bounded by delta F, because that's just how delta F is defined. So then we will have this quantity as a whole is equal or less e to the power epsilon. So this shows that if we actually add Laplace noise to the true value of f, then the resulting output is indeed satisfying differential privacy. So this is one case. This is just a proof, and I will want to show you that it is how we actually use this Laplace mechanism on a simple example. So we have a data set D, and then we are interested in releasing the sample mean of this data set. So this is just a data set that has one variable. And then we have to, so in here, we have to make the assumption that each record is a scalar value between 0 and 1, so it's bounded. And then we calculate the global sensitivity of F. Again, this is the maximum change by changing the value of one data record. So because the data records belongs to 0 and 1, so the supreme will be 1. And then since this is the mean value, so we have the numerator n. And then according to this Laplace mechanism, which says that instead of just releasing the sample mean, which has privacy concern, then we add Laplace noise. So the Laplace noise will center at 0, but the variance is determined by the sensitivity in the numerator divided by epsilon. So epsilon is the privacy budget. So using this Laplace mechanism, which says that we output the raw sample mean that you calculate plus this z from the Laplace distribution, where the variance is determined by the sensitivity and the privacy budget. And then the question comes, how about we have like a continuous value that's not bounded? How we use this Laplace mechanism? So this is actually still an open question, even though differential privacy has been concept that's well used, but still you have to, for any continuous value, you have to somehow like truncate the values into a bounded interval, so then we can carry out the differential privacy protection, just because it depends on the sensitivity, and then it has to be a bounded value. So this is just a general introduction of the differential privacy, and then the next question is, so this is another example that's more related to the talk that I'm going to talk about. So here we have actually binary. So we have a data set that has binary values. So this x1 to xn are the n sample values, and then each of them is either taking value of 0 or 1. And then we actually want to show that the released y1 to yn, which is considered as the synthetic value of the original x1 to xn, satisfy differential privacy if we randomly decide whether the y is taking the original value of xi or its opposite value. So again, if we let this probability to be e to the power epsilon divided by e to the power epsilon plus 1, and then the epsilon here is the privacy budget, then we want to show on the next slide that it is indeed, if we do this random, so they call the random response, because either the original response or the opposite values, then it is indeed satisfying differential privacy. So one thing we want to memorize in here, which is useful for the later proof, is that either you release the true value xi or 1 minus xi with this probability. Okay, so this is just to show you that's indeed the case. So remember, in order to show any mechanism that satisfies differential privacy, we have to show the probability that you have the same result, whether you work with x prime or x, where x prime are the two neighbor data set, will be bounded by this e to the power epsilon. So this is our goal. And then, so first of all, we consider the output of this algorithm being just a synthetic data set, y1 to yn, instead of the original x1 to xn. And still we have to consider two neighbor data set. And then for the purpose of this proof, we assume that these two neighbor data set, x and x prime, have the same sample size, and then they differ by 1, means that they just one for one particular record. And here we let I to be the position of this record. So xi and xi prime only differ in this particular value, but the rest of them have the same value. So then you can imagine if they are releasing because this RR epsilon, this is the random response mechanism. If we want them to release the same data set y, and then the ratio of them will only differ on this i's observation, because because this is releasing the same output, the same synthetic data set y, and then the original data set differ only on the i's observation. So then this ratio becomes just the ratio of these two probability. And also because we have when we decide how we release the value, we do have the conditional independence assumption, meaning that whether we release yi or not only depend on the xi value. So so then we will have this ratio being equal to this. And then you can easily verify that this ratio is upper bounded by the ratio of the probability, these two probabilities. So the easy way is just to, so for example, because xi prime xi differ, so xi prime xi differ, and in this particular case, xi prime can only take the value of 0, 1, and then you can just look at, so there are only 4 possibilities. So xi prime being equal to 0, and then xi being equal to 1, and then they release the same value y be equal to 1 or 0. You can just easily verify this ratio actually is at most e to the power epsilon. So, and then the previous mechanism already tells us what's the probability that if xi equal to 0, and then the probability yi equal to 1 will be just given by these two probabilities. So everything in here is already known. So then you have the 4 possibilities, and then it turns out the maximum one is just e to the power epsilon. So again, this is to show that if we have a private data set X, and then you release the synthetic data Y1, Yn according to this random mechanism, then it is also satisfying differential privacy. So this is actually how we protect our data when we actually trying to estimate the quantiles. So I will show you that in a few minutes. So there are also some very good properties about differential privacy. For example, so if you have already an output that satisfies differential privacy, then any functions based on that output also satisfy epsilon dp differential privacy. So this nice property is known as the post-processing property. And then the privacy loss is or the privacy budget is guaranteed once you set the parameter epsilon, and then that guarantee doesn't require any assumptions about attacker. Recall that in traditional statistical disclosure control framework, we do have to assume something about how much information the attacker already know. But here we don't need any assumption. So even in the worst case scenario where the attacker already knows n-1 data records, then this mechanism allows us to still protect the value of the last observation. So the amount of the privacy loss is quantifiable in the sense that it is determined, or is in the form of a privacy budget epsilon. So, and then this actually relate to the next composition theorem, which says if you want actually multiple release of additional information. So for example, if you want the mean and the median, maybe some additional information based on your data set, then you actually have to do like a multiple release. And then there are also composition theorems to tell you how much guarantee that eventually you have for this multiple release of the information. So say if you have algorithm M1 that satisfies epsilon 1 differential privacy, and then later you want to do another query, meaning you want to obtain maybe another summary statistics M2, and then the multiple release M1, M2 as a whole is epsilon 1 plus epsilon 2 differential privacy. And then this also generalized to the general case where you have k number of release, and then eventually this multiple release as a whole also just satisfy differential privacy, where the privacy budget is the sum of the individual ones. And then I have a longer background info, so probably I talk too much about the background, but then this is actually what we want to do in this quantile estimation. So we know there are many advantages of why people are looking at the quantiles instead of just the mean when they want to understand the distributions. So it is robust to the outliers. And also when we cannot obtain the CDF of the distribution, this is still give us a better ideas than just the mean in terms of how the distribution would look like. And also we know nowadays the data often arrives in the online setting or sequentially. So also sometimes we have to actually divide the sample into different units because we don't have the capacity to store all the data sets. So for that reason, online learning is a popular approach nowadays. And then also because more and more often people are interested in learning a more complex algorithm, so this SGD is becoming popular. So it's actually a natural approach when we deal with the online learning problem, and then we can update the estimates recursively whenever there's a new batch of data comes in. So in the literature, we already know how the SGDs, the stochastic gradient descent approach converges, and also people have already studied its asymptotic inference very thoroughly. But the issue is that how do we obtain the quantile estimate using SGD with differential privacy guarantee? And particularly in this work that we actually focus on local differential privacy. So this is like an extension of the original differential privacy in the sense that we actually each of the users or individual don't actually trust the curator. So in the traditional framework, we always say we have a curator where user trust. So the leakage of information happens when the curator actually release some summary statistics to the public. So this is where we impose the differential privacy mechanism, because we don't trust the public, but we still trust the curator, where we transfer our data, or where we store our data. But in some extreme cases where the users don't trust the curator, meaning that we are not comfortable even to upload our data point to this curator, to this server. So in that case, we have to impose some kind of differential privacy mechanism to the individual data before we transfer our data to the curator. So because this emphasizes that each individual user, so we have this new name, local differential privacy, to emphasize this is the case where each individual user don't trust the curator. We have to impose some kind of local differential privacy. So then we can still protect the individual data. So this is the differences here. So it's still a differential privacy mechanism, except that you can consider this is the mechanism where we protect a data set using differential privacy mechanism, but in this particular data set, there's only one data point. So we look at an online estimation algorithm to estimate the quantile using a stochastic gradient descent SGD algorithm under the local differential privacy guarantee. And then we propose an estimator which is consistent. And then also through this self-normalization technique, we are able to derive a asymptotic confidence interval for the proposed estimator under differential privacy guarantee. So basically from the estimator to later the construction of the confidence interval, we are using the post-processing property of the local differential privacy to guarantee that the constructed confidence interval also satisfies differential privacy guarantee. So this is just a quick review of what Quantile is doing. So Quantile so for example, in this graph, we have the PDF of this density function, and then the TOS quantile will split the area into two parts, such that below this value, the area under the curve is equal to tau, and then above this TOS quantile, the area is equal to 1 minus tau. And in the literature, we know that solving the TOS quantile of a random variable can be considered as minimize this quantile loss function. And then once we have the observed data, then we can naturally think of solving the quantile by minimizing this empirical risk function. So you can imagine, if this is our goal to estimate the quantile, that the only part that use the confidential information from the individual data is this indicator, this indicator function. So this basically says that we have, so we have actually to protect this particular form. So if we don't, so this actually can be updated. So we use Q of tau to represent the the Taos quantile at each of the iterations. So here we iteratively update all the quantile whenever we have a new data point. So this is just the last step where we update the quantile using the previous value, and then the step function times this gradient. So this is also shows that if we are using SGD, the only information about the individual person is this indicator just this indicator function. So you have, whenever there's a new data, you have to compare whether the individual data is greater than this Taos quantile or not in the previous step. So that actually, it shows that if we want to achieve local differential privacy guarantee using this SGD procedure, the only thing we want to protect is actually this binary indicator function. So because this is a value that's taking that's either 0 or 1, then we are using the existing random response mechanism that I showed you earlier to protect this private information about the individual. So then our algorithm actually takes two parts. So we have the main algorithm, which is just to carry out the standard stochastic gradient descent, but we have a random response mechanism that actually trying to protect the gradient, which is corresponding to that indicator function. So this local randomized compare, this is just to compare whether you want to release so this goes back to here. So whether you want to release the truth that whether your value is greater than this update from the previous step, or you want to use you want to release the opposite value. So we protect that value using random response to achieve local differential privacy. And then when we carry out the SGD, so then we when we calculate, we update the SGD, we replace the value, the raw value, using the perturbed value under local differential privacy guarantee, and then using the post-processing property, we can make sure eventually the final update satisfy differential privacy. But here, in order to actually achieve an consistent estimator, we actually have to get rid of the noise that's due to this random response. So this red square actually tells us how we actually have to make sure the expected value of this random response is still equal to the true value. So basically, this is just like measurement error. We have to get rid of the misclassification error in order to obtain the consistent estimator, and then those are the values. So later on, this, because we want to construct a confidence interval, so this green circle contains the values that we need later on to construct the confidence interval. So it turns out that this is something, like I said, this is already known that we have already. So if we so this QN is the average of all the iterates of the quantiles estimated using SGD, and it turns out there's known so it converges to so this is known as the functional central limit series. So it's converged to a normal random variable, but then you will notice that there's something unknown, which is the PDF of this random variable X. So in other words, if we know this fx, the PDF of this this random variable, then we already know how to construct a asymptotic confidence interval. But the difficulty also lies in this quantity. So in order to make sure that this confidence interval is also differential privacy, we have to deal with this fx, this CDF term. So in other words, how can we estimate this fx that under the differential privacy guarantee is a challenge. And it turns out it is a more challenging task than the estimating the quantiles. So our solution, and this is also our contribution for this particular work, is that we use self-normalization technique. This is a technique that proposed by Shaw in his 2010 JSSP paper. So the idea is that we design a statistics, which we call the self-normalizer, which is proportional to the nuisance parameter. In this case, is the PDF of our random variable x, and then the pivotal quantity that we eventually use will be the ratio of the original one and this self-normalizer. So then you can imagine that they both depend on the nuisance parameter, and then the ratio will have the nuisance parameter canceled out. So then we will have a asymptotic pivotal distribution that doesn't depend on any unknown parameter. So if we look at the students' statistics, that's actually a special case. That's exactly techniques using the self-normalization allows us to construct the confidence interval. But one issue we have to note is that the construction of a asymptotic pivotal quantity using self-normalization techniques is usually not unique. So then the question how to construct the optimal one is still an open question. So we in this work, we didn't tackle this challenge, but just use this self-normalization technique to construct our confidence interval for the quantiles under differential privacy guarantee. So this is the technical detail. So I don't have much time to go through the details, but the idea is that we define this as our so we define this AN as our self-normalizer. And then later on, if we look at the ratio, so recall in the original estimator, we do have this Qn minus Q term, and then that has a variance proportional to this nuisance parameter. And then once we define this AN as our normalizer, and then we just look at the ratio of them. And then using, so we already have the functional central limit theorem guarantee the numerator converge to a normal distribution. And then, so this ratio, by using the continuous mapping theorem, we can show that this ratio, which first of all doesn't depend on nuisance parameter, and then also it converges to a normal distribution. So we cannot obtain the exact form, but the quantiles of this asymptotic distribution actually can be obtained using Monte Carlo simulation. So if you're interested in the technical details, so it's in the paper, but here I want to show you that eventually we can construct a confidence interval for our quantile, and then you can tell that in this confidence interval, all the values, the lower bound, upper bound, that no longer contains any values that needs to be protected. So by using, like I said, by using the post-processing property, then this confidence interval also satisfies differential privacy guarantee. Okay, so this is just one simple example to show you that we have, so to show you that our method indeed works. So the blue lines are the point estimate of the quantile. So in this example, we are looking at the estimation of the median, and then we have the invisible confidence interval. So so this is actually our benchmark in the sense that we are using the true value of the CDF. Remember, in the construction of the confidence interval, by using the result of the functional central limit theorem, there's some unknown nuisance parameter. And then if we are using the true value of that, we call the resulting confidence interval as the invisible one. And then we have our proposed one. So you can see they are close to each other, but they are very, very close to each other. But when the sample size n is small, there do have some discrepancy, but this is again due to the fact that we have to actually use the self-normalization technique. It's just like using T distribution. When we use T distribution to construct confidence interval, is wider than the one based on the normal ones. So, but otherwise, our methods works very well, except especially in the case when the sample size goes to infinity. So due to the time constraint, I'm not going to talk the details about this experiments, but this is just to show you the coverage property of our constructed confidence interval under 4 different cases. So we have distribution, the data generated from normal, uniform, standard Cauchy, and then this PERT distribution. But again, this is just to show you that we do have the estimated value close to the truth, and also it has like close to the truth empirical coverage. Okay, so that's all for my talk. Thank you for your attention.
Hey, thank you so much, Dr. Jiang, and let's move to the Q&A session.